Number theory is the study of integers and their relationships, divisibility, remainders, and the hidden structure underneath ordinary arithmetic. For integers a, b, and n, where n is positive, we say a is congruent to b modulo n, when n divides evenly into the difference a minus b. In plain terms, a and b leave exactly the same remainder when divided by n. The greatest common divisor, written GCD of a and b, is the largest integer that divides evenly into both a and b at once. The first key theorem is the GCD-LCM relation. GCD of a and b times LCM of a and b equals a times b. Next, the Euclidean algorithm gives a mechanical, guaranteed way to find any GCD. GCD of a and b equals GCD of b and open bracket a mod b close bracket. You keep repeating this replacement until the remainder hits 0, and the very last non-zero remainder you computed is the GCD. Bezout's identity guarantees that integers x and y always exist such that a times x plus b times y equals the GCD of a and b. And Fermat's little theorem says, if p is a prime number and the GCD of a and p is 1, then a to the power p minus 1 is congruent to 1 modulo p. Let's sketch why the Euclidean algorithm works. Suppose r equals a mod b, meaning a equals q times b plus r for some integer q. That's just what remainder means. Here's the key insight. Any number that divides evenly into both a and b must also divide evenly into r, since r equals a minus q times b. Going the other direction, any number dividing evenly into both b and r must also divide evenly into a. So the pair a and b and the new pair b and r share exactly the same common divisors, hence the same GCD. Repeat this, and the numbers keep shrinking until the remainder hits exactly 0, and the process stops there. Think of modular arithmetic as arithmetic on a clock face with n numbers written around it instead of the usual infinite number line. You only ever care about the remainder, the position on the clock face, so any two numbers differing by a whole multiple of n are treated as completely identical. Here's the trick. Run the Euclidean algorithm as a simple repeating table. Divide, write down the remainder, then repeat using the old divisor and the new remainder as your next pair. Never guess the GCD by inspection. Compute it mechanically. Worked example A. Find the greatest common divisor of 252 and 105. Step 1. Divide 252 by 105. 252 equals 2 times 105 plus 42, so the remainder is 42. Step 2. Repeat with the pair 105 and 42. 105 equals 2 times 42 plus 21, remainder 21. Step 3. Repeat again with the pair 42 and 21. 42 equals 2 times 21 plus 0, remainder 0, and that's where we stop. Step 4. The last non-zero remainder we computed was 21, so the greatest common divisor of 252 and 105 is exactly 21. Worked example B. Find 17 mod 5. Step 1. Divide. 17 equals 3 times 5 plus 2, so the remainder is 2. Step 2. Therefore 17 mod 5 equals 2. Worked example C. Bezout's identity by back substitution, using the same 252 and 105 from example A. We already know the GCD is 21. Now we find integers x and y satisfying 252 times x plus 105 times y equals 21. Step 1. Start from the second to last line of the Euclidean algorithm. 21 equals 105 minus 2 times 42. Step 2, we need to eliminate that 42, so go back to the first step. 42 equals 252 minus 2 times 105. Substituting this in, 21 equals 105 minus 2 times open bracket 252 minus 2 times 105 close bracket. Step 3, expand this out carefully. 21 equals 105 minus 2 times 252 plus 4 times 105. Combining the 105 terms, 21 equals 5 times 105 minus 2 times 252. Step 4, reading off the coefficients. X equals negative 2 and y equals 5. Satisfy the equation 252 times x plus 105 times y equals 21. As a final check, substituting back in 252 times -2 plus 105 times 5 equals -504 plus 525 equals exactly 21, confirming the answer. Common mistakes to watch for. First, stopping the Euclidean algorithm one step too early. Remember, the GCD is the last non-zero remainder you compute, not simply the last remainder you happen to write down. Second, sign errors during back substitution for Bézout's identity. It's easy to drop a negative sign while expanding brackets, so always double-check your final x and y by substituting them back into the original equation, exactly as we did in example C. And third, applying Fermat's little theorem when P is not actually prime. The theorem's guarantee depends entirely on P being prime, and it can simply fail for composite numbers.